So, today's lecture will be about logic, and logic, as we see in mathematics, is a very, very crucial part, especially in something like proofs, even your booleans, and even in CS. So, logic basically comprises of let's say, some statements. Now, what are these statements? Each of these statements refers to some sort of mathematical proposition that you have. Now, what do I mean by a mathematical proposition? If I say that for every n belonging to natural numbers, if n is even, then n cubed will be even. Now, this is a mathematical proposition because I'm proposing this as a mathematical statement. Each of these statements will have a true or a false value. A little thing to notice here is that, like, false statements are also statements. So if you get a question that is this statement, like if you're given some sort of an expression and they ask you if this is a statement or not, even if it is false, it is still a statement. This statement that we've taken, this is in particular in English, and each element of this statement can be represented by mathematical symbols, and that representation of mathematical symbols and how you evaluate those mathematical symbols will form your basis for logic, right? So if we just get rid of this for now, we can work on some of the symbols we have. So symbols in general, we have any statement, you need to convert it to mathematical symbols, right? Because you're always going to find it easier to work with symbols once you understand the meaning. So the first type is going to be quantifiers. Now, you have always been like introduced to the idea of variables and how variables work. So quantifiers basically it comes from the word quantify, which is how you're quantifying and using variables, right? So anything like for every, for some, there exists, every, for any, all of these, etc., are quantifiers. So they quantify a variable. In particular, we learn about two which are most commonly used. This inverted A, which stands for all or for every. And we have this laterally inverted E, which stands for there exists or for some. Now, in particular, these two quantifiers can be used in a given context. They have their specific use statements in given cases. So if you have for all x belonging to integers, x is either odd or x is even, which is true, right? We know that every possible integer is either odd or even, right? So usage for all. What else we can do? There exists. So we can say that for all x belonging to real numbers, there exists some y. Like for each and every x, for every x there exists in real numbers, this symbol belongs, this is literally read as belongs to. And it's written as an epsilon. And yeah, so there exists some y belonging to reals such that x is less than y. What does this statement mean? You don't need like set brackets here, right? This statement basically says that there exists some y, there is some y for every x such that x is less than y, which makes sense, where x and y are real numbers. This makes sense. Why? Because like for every possible x, for every real number, you will always have another real number which is greater than it, right? This is what it means, right? Because x is smaller, y is greater than it. Yeah. So that's it, right? And that is what we have for quantifiers. The other type of symbols we have are called connectives. Well, if you look at this statement here, there's an or here, right? Now this is a connective. What are connectives then? So if I say that you have, let's say, okay, so let's just start with some examples, right? There are like and, or, not. These are not is not technically like in connective, but and is denoted by this symbol, or is denoted by that, and not is negation, which is denoted by that or that. In front of a statement, we'll say it's not. So if I say that A is a random arbitrary statement and I have B, which is another given statement, and let's just say that this one is true and this one is false, right? So, and, which is similar to intersection if you're familiar with the concept. So this will basically say if you have A and B, this is literally read as statement A and B. So it's asking me if A and B are true. And because like intuitively, if you think about it, if A and B both are true, only then will it true. If A is true and B is true, else it will always be false, right? So if I make something called a truth table, what is a truth table? A truth table basically tells us all possible values of A and B and their composition using some connective slash implication slash, we'll see what implications are. So all possible values are going to be true, false, false and true, true and true, false and false. Now what you need to know is like the best way to go about these is memorize them and have some intuition about what and why, right? So if you have true and false will always be false. False and true will always be false. True and true will be true, and false is always false. And you will have to memorize these at some point because that's crucial, right? And these basic levels of combination and composition of different statements is what forms the basis of some really complex statements, because at some point you will be asked to evaluate something like A and A or A and or B, right? Something like this. And you can have multiple statements. You can have some statement C here and you can have some statement D here. And each of these you'll have to break up into parts. You will find D or B, and then this thing you will combine with C, whatever C is, and take an OR between these two, and then whatever you get finally you will have to combine with A. So that's how like stepwise you will be able to work with these multiple sort of composition of various kinds of statements. What else we can do at this point is see what does OR do. So OR in itself is similar to AND yet very different. So if I ask you A or B, when is A or B true? Well, it says OR, right? So when either A or B is true, it's gonna be true, right? So if I take this first condition, A or B, true or false, has one truth, so it's going to be true. False or true is going to be true, true or true. It has one truth, true, and false or false. So out of false or false, it's always going to be just false, right? That is what we have for your OR statement, right? Which is similar to the union, for example. So that's it. And what else do we have for negation? Negation basically means whatever you have as a Boolean value, whatever true or false value you have, it's just negative of that. So it's just the opposite. So for practice, let's do negation of A, and let's do negation of A and B, right? So what will we get? We will have, we know negation of A. Let's just look at A for now. So what's A? Here, it's if A is true, negation of A is going to be false. If A is false, negation of that will be true. True will give false, and false will give true. The next case is the negation of A and B. Now, it does not make sense to calculate A and B again when we already have calculated it right here. So let's just use this and find the negation of whatever this is, right? So if A and B is false, negation of A and B will be true. If it's false, it'll be true, false here, and true here. Perfect. So that's what you have for negation. There's also some other kind of statements. Something which is really important and really comes to mind when you talk about logical statements and logical proofs is implications. Well, what are implications? Implication basically comes from the word imply. So, and it's denoted by this symbol, right? So when you think of an implication, if I say that P implies Q, this basically means that this happens, and then as a result of which this happens. And here P is always going to be our hypothesis. This is just standard notation, whatever they call it. And this is your conclusion. So your hypothesis leads to a certain conclusion. And the way I like to think of it is a promise. So say, so if you get a 90% in math, I will buy you a Ferrari. I don't have money, but yeah. So usually all implications, not usually, actually all implications are of the form, any P implies Q is of the form if P then Q, right? And an if then statement is always going to be an implication. And if I want to draw a truth table for this, let's just make this a little bit smaller so that we have more space, right? So if I have a P, a Q, and another column for P implies Q, what will I get? Let's just try and, this is an amazing color, very tacky though. Yeah, so if I have all possible values, which is TF, TF, TT, FF, so this is a standard sort of way to find out all possible values. And here we go. So using this as an example, we can always derive a truth table for any sort of implication, right? So this is how I like to remember if in case I get a weird question that it just confuses me to no end, right? So if I get 90% in math, then I will buy you a Ferrari. Fine. Okay. So here the hypothesis is true, P is true, which means that I got the 90% and I bought you a Ferrari. You got the 90% and I bought you the Ferrari. So the promise is held, right? So this is going to be true. If you don't get the 90% and I still buy you the Ferrari, if you don't get the 90% but I buy you the Ferrari, the promise never actually happens because the hypothesis does not happen. So this is always going to be a true statement because it's never actually dependent on what the statement actually is. So it says if the emphasis is on the if right now. So if something doesn't already happen, there will be no consequence of that. There will be no conclusion based on it. So the consequence does not occur. It's actually not, oh god, I can't spell. So it's not dependent on whether the consequence occurs or not. And same goes for this case, because here too, the hypothesis is false. So both of these statements are always going to be true, but they won't actually call upon the implication in itself. What they are known as are vacuously true. Right? And this is a very really commonly asked question, because this often ends up confusing a lot of people. So, and yeah, that's it. And what about true implies false? Now, you get your 90%, right? And you really work hard, and then I don't buy you your Ferrari. You're going to be really mad, for the lack of a better term, but you're going to be really mad. And in general, the promise would be broken. So that's false. So the only case where an implication is false is when true implies false. And that makes the whole implication false. So that's the truth table for an implication. These implications are like favorites for proofs and like all sorts of weird questions. You'll end up using these in more and more math as you go ahead. The next and probably I think the last one is an if and only if statement. Now, an if and only if is different from an implication because it works both ways. So it is P double implication of Q. So if and only if P, only then Q happens. And this is nothing but saying that P implies Q happens and Q implies P happens as well, because like there's a reverse implication as well, right? So, well, these statements are if and only if type, like the implication is an if then type of situation and an if then sort of statement. We have an if and only if here. So when I try to evaluate this, what do I get? I have a P, I have a Q, and I have a P double implication Q. You know what? Let's just derive it like the old-fashioned way. Let's use this, right? And this we know is like equivalent to this. We'll learn about equivalences in upcoming lectures and what like being logically equivalent means. What you can know for now is like they just have the same truth tables. So let's just break this up. Let's put this in one end, this in one part. Let's call this P implies Q, and this is going to be Q implies P, and this is going to be P implies Q intersection with or and Q implies P happening simultaneously. Now, having this means that we evaluate P implies Q first, and we imply Q and P. So Q implies P happens, and then we take the AND statement, right? So if we have a true, false, true, false, 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 true, true, what do we get? We have a P implies Q, which means true implies false. Note that the only condition when true implies false is when the implication actually becomes false, right? So here we have true implies false, so this becomes false. False implies false is true, vacuously, but true. This is also true, this is vacuously true, but still true. What about the other way now? Q implies P. So we go this direction now. So from the truth table, we can say that false implies true, which is vacuously true, but still true. False implies false, which is going to be true, vacuously, but still true. True implies true is always true, and true implies false is the only case where an implication is false. Now, we have this case where we take this thing, this first and this second, and we use this first and this second, and we take an AND statement between them. Now, AND, we remember, is when both of them are true, only then is the AND statement true, else it's just false. So if we look at, what are we looking at right now? We are looking at just this, and we are looking at just this, right? So if I say that we have something like false and true, what would you say? It's just the same thing as that. It's just in a more complicated form. I can call this statement as R, and I can call this one as something Q, maybe. No, we have already a Q. Let's call this S. So this statement will just become R and S. And while evaluating this, we can just use an AND operator between two of these values. So in each case, false and true will just be false. True and true will be true. True and true will be true. And true and false will be false. So that is your truth table for a double implication. And because we just said that this is equivalent to a double implication, we can rewrite in the form of, let's just rewrite it first here. Let's just say this is P implies Q and Q implies P. And this is the same as P, Q. And this is false, true, true, false. And what are P and Q though? P and Q are these values right here. Note that the order can be changed and order does not matter in the truth table. It's just these specific Boolean values that matter. And out of here, you can just derive any sort of values or any sort of statements that you can come up with. And those can be defined using just whatever you want. Also, there are some really nice questions that can be made around this. And hence, there are some propositions that you can test out and see if they are logically equivalent, right? So what I want you to check is, first is negation of P implies Q. This is a formula, and this is basically used everywhere, right? So your implication is just the implication, the negation of an implication is an AND statement. Now, what does that mean? So this means that like this implication and the negation of that implication is an AND statement. And this statement is written as P and negation of Q. Now, what you will do is like you'll draw the truth table for true and for P and Q. You'll put in all the true false values and you'll see the negation of P implies Q, and the truth table for P and negation of Q will have the same Boolean values here and here, and hence they'll be logically equivalent, right? And that's all that logically equivalence means. So it's really easy. There's another really good question that you can try out, which is the P implies Q and negation of Q implies negation of P. Now this is actually something called a contrapositive, which is actually used as a proof strategy, to be honest. And proving this really will help you give some really good insight on how a true and a false value can really work themselves out and how both of these are going to be logically equivalent. Also, what you can test out is the negation of an AND statement. P and Q negated, and negation of, oh, my bad, negation of P or negation of Q should be logically equivalent, right? And the negation of an AND, some people will like to read this as not P and Q is the same as not P or not Q. This is all that is saying for all those computer science and math students out there who understand this thing better. This is all this is saying. So again, you'll have to make the truth tables, you'll have to derive the values, And this is where I leave you for now. The next video will cover some really nice proof techniques. We will be using these things a lot. And that's it for this video. Thanks for watching.